Okay, let's talk about collisions. This is really where conservation of momentum shines. Okay, so here's the thing. A collision is when two things bump up against each other. And if you think about it, momentum must be conserved in an interaction like this. Here's why. Let's look at this object here. This object is traveling at 3 meters per second. This one's traveling at 1. So they are going to collide. And when they do, the force that this one here places on this one is going to cause it to move forward at a faster rate. But that same amount of force is going to be applied backwards on this one, causing it to slow down by the exact same amount because the same force acts for the same amount of time. So I get the same impulse, but in the opposite direction. So no matter what, anytime two objects collide, regardless of what happens to their energy, there's always going to be a conservation of momentum. Whatever the momentum is here, in this case, it's 4 kilogram meters per second, it's what it's going to be afterwards, always. But that's not going to be true for kinetic energy. So don't get suckered into this. College Board loves to give you situations where you think, I'm going to solve this using conservation of mechanical energy. Hang on a second. That only works when you have conservative forces. And it turns out, usually when two objects collide, there's like a normal force when one surface bumps up against another one. And that causes atoms to jiggle as a consequence of that. And so they end up dissipating some of that mechanical energy as heat. So in most cases, when collisions occur, kinetic energy is not conserved. It goes down. All right. So look at this case here. So when these two collide, like we had, this is exactly what we had before. We saw their momentum was conserved. But now look what happens to their kinetic energy. I have 1/2 of 1 times 3 squared. That gives me 4.5, plus 1/2 of 1 times 1 squared. So that's a total of 5 joules here. But when I do the same thing over here, I see I only have 4 joules. 1 joule of energy gets dissipated as heat. So I could solve for that just by using conservation of momentum and then applying conservation of energy. But it doesn't work in the other way around. Okay. So the trick is you want to always solve for momentum first and then figure out what the energy situation is based on the velocities that you got from that. Now, it is possible to contrive a situation in which the collision is the force between the objects is a conservative force. Like if I put a spring here or magnets, those are the two things that we physics teachers like to do to cause our collisions to be ones in which the kinetic energy doesn't change, and we call these a perfectly elastic collision. So the idea here is, it's what we had before, right? The exact same thing before. We had 5 joules of energy, but I put a spring on this one now, massless spring, right? During this collision, as this is applying a force here, that force is compressing the spring. So the energy is being converted into um, spring potential, and it's getting re-released as kinetic. So at the end of it, these objects still have the same amount of kinetic energy. I haven't changed what their the total momentum is still 1 times 1 plus 1 times 3. That's 4, which is what it was over here. I didn't change the momentum. Can't, but I did conserve the energy. And when this happens, it's called a perfectly elastic collision. So I just want you to think perfectly elastic collision means kinetic energy is conserved, which means the force of interaction between the two colliding objects must have been a conservative force. In the case of collisions, it's hard to come up with something other than spring or magnetic. And I know we didn't really talk about magnetic forces being a conservative force, but it is because you can have, remember, because, well, anyway, it is a conservative force. Okay, I'll let you worry about that when we get AP Physics 2. So again, so the idea is in a perfectly elastic collision, I'm just going to walk you through it. Okay, so I have these two objects colliding with each other. And if you look, 1 times 1 in the positive direction, 1 times 1 in the negative direction, the momentum is 0. Okay. And but the kinetic energy is 1/2 plus 1/2 is 1 joule. Now they're going to come together with a spring, momentarily stop. And when they stop, I've got 1 times 0 plus 1 times 0. My momentum is still 0. But now what happened is my kinetic energy is 0. Now I screwed this up. I put UG is really US. Sorry about that. So the spring potential energy is where all of this now is. And then that gets released and it pushes outwards. And when it does, this ends up going in the negative direction. This one goes in the positive direction. I end up with 1 times -1 plus 1 times +1. It's still 0. Notice I never changed my momentum, but now if I do my math again, I'll see that I still have 1 joule of kinetic energy. So my mechanical energy never changed. As these lost kinetic energy, they stored it up as potential and they re-released it as kinetic. So the mechanical energy remained constant because none of it got dissipated as heat. But then we can have the opposite of that, which is a perfectly elastic collision. Now, perfectly elastic doesn't mean all of the energy is converted to thermal. It can in this case. It just means that we have the maximum possible decrease in kinetic energy while still maintaining conservation of momentum. So if I take those same 1 kilogram objects from before, have them go at 1 meter per second like I did before, but now they're going to collide and stick together, then what happens is, the momentum was zero beforehand, the momentum was zero afterwards. However, I noticed I went from having 1 joule of kinetic energy to 0 joules, and all that 1 joule of energy got radiated away as heat. The atoms just vibrated when they collided with each other. Now, what perfectly inelastic means, though, is that they stick together afterwards. That's when you hear the word perfectly inelastic. I want you to just think that means they collide and stick together. College Board likes to give you a situation where they say like two cars collide and their bumpers hook together, or spaceship A docks with a spaceship B. Right, they're joined together as one object, or there's Velcro or tape on an object, so when they collide, they stick together. So perfectly inelastic means this situation where they stick together afterwards. A partially inelastic collision means they don't stick together, but the forces acting on them are non-conservative, so some heat does get dissipated as heat. So again, I'm going to use the same 1 kilogram traveling at 1 meter per second. I have zero, once again, I have zero net momentum of the system, and I have 1 joule, right? But then they bounce off each other's case. This one ends up going this way at 1/2. This one goes that way at 1/2. I still have zero. I've still conserved momentum, but now I notice I have half as much kinetic energy as I had before. So to reiterate, in a perfectly elastic collision, the energy I start with is the energy I end with because the interaction occurred through conservative forces that stored the energy as potential energy and then re-released it, usually as a spring or magnet. In a partially inelastic, it means I've lost some of my kinetic energy. The objects collide and bounce off each other, but they don't stick together. And a perfect elastic means they stick together, which means I'm going to get the maximum amount of kinetic energy loss that is possible while still conserving momentum. Now I want to talk a little bit about how to interpret velocity versus time graphs to analyze collisions. This is an important skill in AP Physics. It comes up quite a bit on the AP Physics test. And the good news is, if you pay attention to what I'm about to tell you, it's really not that hard. It really isn't, okay? But if you don't, it is. All right, so here we go. So basically, I can tell two things by looking at this. I can tell what the relative masses of the two objects are. And on the AP tests, they don't have colors. Like this might be a dashed line and this one not, okay? But I can tell what their masses are, and I can tell what type of collision it is, whether it's a perfectly elastic, perfectly inelastic, or partially inelastic collision. Let's see how I'm going to do that. So the first thing I'm going to do when I look at this, I'm going to say I can always tell anytime I have a velocity versus time graph of a collision, I can always tell what the relative masses are, and here's how. If I look here, this object here changed its velocity by 1/3 of what this one did. That means this one has 3 times the mass, or conversely, this one has 1/3 the mass because it changed its velocity 3 times more. Right? Look, 1, 2, 3, and this one changed by 1. Okay, and so I can tell that the blue one has 1/3 the mass of the red one, and I can tell by looking afterwards. I look at the difference between their velocities, and they have the exact same velocity, which means they've joined together. So this is a perfectly inelastic collision. So those are two things I can tell. The fact they stuck together tells me what kind of collision, perfectly inelastic, and the changes in their relative velocities tells me what their relative masses are. Now here's another one. I look at this one here. Let's just start with this. They didn't stick together. They don't have the same velocity. But the velocity changed. I look, this gap here is definitely bigger than this gap here. Like the gap between them shrank. It didn't shrink to zero, but it shrank. So that tells me this is partially inelastic. But I can still momentum is still something I can tell. So I look at the momentum. This changed by 1, 2, 3 units. This one changed by 1, 2, 3 units. They have the same mass. So looking at the change in the velocities tells me what the relative mass is. Looking at the change in the difference between their velocities tells me what kind of collision. That tells me about the energy of the situation. So let's look at a perfectly elastic one. When I look at a perfectly elastic collision, what I notice is this. First of all, momentum is going to be conserved, so I can tell which objects, how their masses compare to each other. This one changed by 1, 2, 3, 4. So from here to here is a change of 4. And this one changed by 4, 8, 12. So I know the red one changes velocity 3 times more. So it must have had 1/3 the mass. Okay, it's just Newton's second law. But now I look and I see that this distance here between the initial velocities is 1, 2, 3, 4, 5, 6, 7, 8. Here it's also 8. So since there was no change in this distance here, that tells me there was no loss of energy. And therefore, I know that this is a perfectly elastic collision. So that's a really helpful little trick to use. What about this? All right, first of all, I can tell that the blue one has half the mass of the red one because it changes velocity twice as much. Okay. But I can also see that, wait a second, the distance, this gap between these two afterwards got bigger, meaning there's more kinetic energy there than there was before. Is this possible? Sure. It means there was energy stored. So like I collided with something that say had a spring or an explosive. So no matter what, you have equal and opposite forces at all times. The momentum is always going to be conserved. But the energy usually goes down. The kinetic energy usually goes down. In a perfectly elastic, it can be conserved, and I can contrive situations like this where it actually goes up because I released, stored spring energy, for instance. Okay, now the last thing I want to do is kind of tricky, and I will say it is very unlikely that on your AP test you will actually have to quantitatively solve for the velocities of a perfectly elastic collision. They have asked that before. They usually don't, but let's just walk through it because it's kind of cool, quite honestly. Okay, so here you go. I've got a 2 kilogram object traveling at 3, a 1 kilogram object traveling at 2. They're definitely going to collide, and I'm told that what happens is, oh, I'm sorry, this is partially inelastic. Never mind, we know how to solve these. Okay, so we're just gonna, if I know what this velocity is, I can find this one just by using this equation here. Sorry, I started on the perfectly elastic thing. Uh, and so I just have to substitute in each of these values and solve for the unknown velocity. That shouldn't be hard for us to do. Okay. If it's perfectly inelastic, again, it's very simple, except I just remember that I only have one final velocity, so I can group these two masses together and use this form. Right? I'm just basically saying, well, since I only have one velocity afterwards, I could use that other equation. It's just a little bit more convenient to do this. And I see I have this for my final velocity. All right. However, all right, what I just said, solving elastic collisions is challenging. It doesn't usually come on the AP test, but you can do it. So let's just try. Let's talk about it. Okay. So one way of setting up is say, look, in a perfect elastic collision, both momentum is conserved and the kinetic energy is conserved. So these two are both true. So we could mathematically combine these equations, and when we do, we'll end up with this, which isn't that hard. If anything, the initial velocity of object 1 plus the final velocity of object 1 is equal to the initial velocity of object 2 plus the final velocity of object 2. But you know what? If we look at a graph, it makes so much sense. Look at this. Okay. I look here, I know it's an elastic collision because this gap and this gap are the same. Now, if you think about it, so if I say V1 initial minus V1 final, I'll get a value of 2 plus 0. Okay. If I say V2 initial plus V2 final, I'm going to get negative 2 plus positive 4. That also equals 2. They equal each other. Okay. So knowing that gives me a very easy avenue to solving it. I mean, me personally, I'd memorize this. And if I don't memorize this, I would just take it off of here. Okay. You could also say this one minus this one equals this one minus this one. Either way. Okay. Now, let's just try it and then we'll be done. Okay. So what if I have the same thing I had before, but now I'm told, you know what, in this case, it's perfectly elastic. All right. Well, here's what I know if it's perfectly elastic. I'm going to use this. I'm going to say if I take the sum of the objects one's initial and final velocity is going to be equal to the sum of objects two initial and final velocities. So I happen to know what the initial velocity for each of them is. I don't happen to know what the final velocity for each of them is. So I know that this is 3. I know this one here is 2. I know what these are. But guess what I'm going to do? Maybe you already figured out. I'm just going to take this and rearrange it and say, well, I could solve for VF1 in terms of V2F. All right. So I'm going to say, well, if I rearrange this, I get this. Right. which tells me that the final velocity of object 1 is equal to the final velocity of object 2 minus 1. And now I can simply substitute that into this equation, and I can figure out what the other one is. So let's just try this here, all right? So I know that this is, I'm going to use this equation here. I'm going to say I have a mass of 2, velocity of 3, a mass of 1, velocity of 2, a mass of 2, and a velocity of, well, I said, you know what? I've decided to call VF1 this. So I'm going to put that here, equals 1 times VF2. And now since I only have one unknown variable, I can solve for it, and I get this. It's 3.33. Okay. Now I can take this and I can substitute that back in to this equation here. All right. Or I can do it this way. Sorry. I can just substitute it this way and say, well, this is 2 times 3. This is 2. And now I end up substituting this value for VF2 into here. Oops, I got a student I'm talking to. All right. And if I solve this for VF1, I get 2.33. Now, I should double check. Did I do it correctly? If I did it correctly, the sum of the momentums beforehand has to equal the sum of the momentums afterwards. And if I solve this, it's 8. If I solve this, it's 8. Okay, so there you go. We have 3 constant collisions. We always conserve momentum, but we don't always conserve kinetic energy. Thanks for watching.